In this part I'm going to show you how to calibrate a pH meter. As you can see here, we've got calibration solutions. These are standards: pH 4, pH 7, pH 10. You'll notice that they're all different colours. We're going to choose to use the pH 7 to calibrate our pH meter. Alright, so now we're looking at how to calibrate a pH meter. So I'm putting the probe in here into the 7 buffer. I'm going to pull this over here so you can see the measurements and what I'm doing on the screen here. So what I'm going to do is I'm going to hit Cal Measure here, and that will change this to calibration here. Now you can see that it says 7.26 and it's down here it says 7.00. So that's what it's actually going to hold on to, will be that 7.00 once I hit enter. So I'm going to hit enter, and there you go, it's at 7.00. Don't worry about what this is doing down here. Just hit Cal Measure again, and you're ready to go with the measurement on your next solution. So rinse off the pH meter into a beaker with some DI water, and then you can put it in your next solution, or you can put it back in its house. So this is part A of the buffer and pH lab. So what Eve's going to do is find the pH of an NaCl solution. All of these beakers here are labelled, and we need about 25 mils. So she's going to pour about 25 mils in. We don't need exactly 25 mils, so she's not going to be too concerned about how much she's putting in there. She's going to eyeball it. That looks good, Eve. That's excellent. Right, go ahead and pour that into the beaker, please. You'll notice that we've lined these up behind the beakers as well to make sure that we don't mix up our solutions. Would you please turn on the pH meter? The pH meter gets turned on by the on-off switch. Now this has already been pre-calibrated, so what Eve is going to do, could you bring that into the shot please, Eve?
Yes. Or wait, this?
No, the probe, you're good. Alright, so what she's going to do is she's going to unscrew the bottom part from the bottom of the probe there. See, it's a little screw cap jobby there. Oh, is it not coming off? Alright, you can just pull it off then. There we go, that's alright, that'll be fine. So you can either unscrew it or just pull it straight off. I prefer to unscrew it, but if it doesn't unscrew, obviously, that's alright. So go ahead and stick that in. So what Eve is going to do, now just leave it in there, please. So as long as you've got about that volume in there, it should be enough to get a measurement on the probe. So you wait for it to stabilize, and if it's still not stabilized after a minute, just take whatever measurement it happens to show there. So Eve's going to write that down. Don't worry about saying what it is, just go ahead and write it down. So now what Eve is going to do is she's going to make up the next solution. So she's rinsing out the graduated cylinder a couple of times with water. There we go, to avoid any contamination. Don't worry if there's any water in there. It doesn't matter if it's a little bit wet. The molarity here is not really that important. What matters is what's in the solution. So again, Eve is going to make up this next solution. Again, she's not being too concerned. That's good enough. All right. Yeah, let's go ahead and stick that in. Yay. Alright. Now what Eve is going to do, instead of just taking that probe and sticking it straight into the second solution, she's going to do what she's doing there, shake it off a little bit, bring it over to the waste beaker and rinse the bottom of the probe off with DI water. Then she's going to go ahead and stick the probe into the next solution. There we go. And that process is going to be repeated a couple of times, and of course they're going to mark down whatever result they get off the pH meter here. Okay, now Eve's going to put the pH meter away now that she's gotten her full results. She's going to rinse it off with DI water, and then she's going to put it back in its little house. There we go. Just push it straight in. and make sure that the probe is close to the bottom. There we go. It is. Excellent. Well done. So now what Eve's going to do is she's going to add 2 drops of Brom Cresol Green to each of these solutions. And as you can see, we've still got the beakers lined up, so we know exactly what's what. It's good. Okay, so what I'd like you to do, Eve, is just give each one a light swirl. So you'll notice you can get different shades here as well, so those should all be recorded too. Alright, now what Eve's going to do is she's going to pour each of those solutions into the waste container here, the waste beaker, and then you will follow the instructions of your instructor about how to dispose of that waste. So what I want to do here is give you some help with part A, especially the net ionic equations, because that seems to be worrisome to a lot of students. So let's go ahead first and look at the pH scale. And what we know is the pH scale usually runs from 1 to 14. And we know that between 1 and 7 we have acid, and between 7 and 14 we've got base. So we already know what this is going to mean here. pH is greater than 9 and pH is less than 5. You're actually going to find pH values for these guys up here, the NaCl, Na2CO3, NaC2H3O2, and the NaHSO4. Now in each of these instances the Na won't really matter because it's going to be a spectator ion, and I'm going to show you what I mean by that. The NaHSO4 at first glance could either act as an acid or a base, but let's first of all talk about what we mean by acid and base. So acid is going to produce H+ in solution, and bases tend to produce OH- in solution. So if you look at those two, H+ and OH-, you can see that by adding those together you'd get water, H2O. So they're different halves of the same thing really, but acid is going to give you H+, base is going to give you OH-. Let's take a look at NaHSO4, and I'm going to show you 2 possibilities for that, and you may use it or you may not use it, I don't know. It all depends on what the pH is going to be here. But we've got NaHSO4, which can be split up into Na+ and HSO4-, and that goes for all of these that have the Na+ as part of their structure. The Na will come off as Na+. So what I'm going to do is I'm going to show you first of all what I mean by Na+ as a spectator ion and why it's not present in the net ionic equation itself. So let's say we're treating this as an acid, and I'll write acid over here. So what we're saying is that the HSO4- will split into H+ and then something as well as Na+. But you can see here the Na+ is going to appear on both sides, so it's going to get cancelled out. But what is this H+ going to be combining with here? Well, it would be SO4 2-. And you can see here that if you add plus and -2, you'll get -1, so that will balance. So that's what the equation would look like if HSO4- was being treated as an acid. Now you'll know if it's an acid or not by looking at the pH up here. I already told you how to determine that based on the pH scale. Now for the base, I'm not even going to worry about the Na+ anymore because I told you that the Na+ is a spectator ion. It's there at the beginning, it's there at the end. That's why it's not present in net ionic equations. But let's say we wanted to treat this as a base. What we would do is we would put it in water because we need a source of OH minus here, and we're not going to get that from the HSO4. And if we were treating it as a base, what we'd get is OH minus, and then it's sort of like the H2O can be considered to be OH minus and H plus together. So we've got the OH minus, the H plus joins with the HSO4 minus, and we'd have H2SO4. So that's how the, I'll just circle this off here. That's how it would look if we were considering that as a base. Alright, so the next one I'm going to look at, I'm going to look at NaC2H3O2. And what I'm going to do is I'm going to split that into its ions, which will be Na plus and C2H3O2 minus. And this one, I don't feel like I can treat it as an acid at all, but if it came out as a base, here's how it would work. I'd add it to water, again just like I did up here. I'll get OH minus, and I'll get HC2H3O2. So you'll see that again I'm considering the OH, the water as being OH minus and H plus together. There's your OH minus. The H plus joins with the C2H3O2 minus, and we get this, which is going to be neutral. See how it does balance as well. We've got negative here. So everything balances for that. We've got one more to consider here, and that's the Na2CO3. And again, I can't really think of how I might present that as an acid, but let me get rid of some of this stuff here. And we'll consider the Na2CO3 here, and it would split apart. If you drew a picture of it, it would look like this: Na plus, and CO3 2 minus, to make that all balance out. So again, if I was trying to treat this as a base, it'd be water plus CO3 2 minus gives, and again we'll consider the OH minus and H plus here, and I will let me erase that H there for a second, since we're trying to make this a base. This is going to form OH minus, and then the H plus will join with the CO3 2 minus, and we'd end up with HCO3 minus. You can see that all balances out as well. You've got negative, and that's 2 minus, so that does fit. And again, you'll notice that the sodium is a counter ion, and it's going to be a spectator ion, so it's going to appear in both sides, and we're just going to ignore it. But that's how you treat that if it was a base. So whether you use these or not is going to be entirely dependent on what the pH up here is. In the NaCl, I can't really do anything with, so it'll give you a clue that you're probably not going to have to do anything with that anyway. Alright, well that's it for part A. Alright, we're on part B now. So what Teresa is going to do is she's going to wash her chem plate. These are chem plates, or well plates as it's sometimes called, and she's got a waste beaker there. She's just rinsing them out, rinsing all the little wells out there with distilled water or DI water. Now these don't have to be dry, but she's going to do her best to get most of the water out. There we go. That's good, thank you. Now the idea here, now you're going to have to move off to the side here, Teresa, so I can get this into the shot. The idea here is that you're going to put 1 milliliter of each solution into a well, and then 1 drop of each indicator solution. It turns out though that 1 milliliter is about half the well, so you just have to fill the well up halfway and then add a drop of the indicator solution. So in this next step, we've already cleaned off the well plate, so now what we're going to do is we're going to put each of these solutions. This first one is HCl, and Teresa is going to half fill each of these well plates with the HCl. Half filling is about 1 milliliter. So she's going to do that for the first row there, because we've got 5 indicator solutions, and you can see them all lined up there at the back. There we go, that's good. And then after she's done that, she's going to take the next solution and she's going to put that behind the HCl. It's going to be more efficient to add all the indicators at once. You'll see what I mean in a bit, because I'm going to film that part of it as well. So presently what Teresa has done now, or almost done, is she's half filled the first row of well plates, 5 of them, with HCl. Now she's going to do the second row, and that's with the NaH2PO4. And she's just going to drop or squirt or whatever that solution into each of those. Then she will repeat the process with the HC2H3O2. So what we've got in the first row is the HCl, and then in the second row we've got NaH2PO4, and in the third row we've got HC2H3O2. First row, second row, third row, and there's 5 solutions to match the 5 indicators. The most efficient way to handle this now is for Teresa to grab the bromcresol green, and she's going to put 1 drop of indicator into the first column there, which is going to be, first of all, the HCl, and then the NaH2PO4, and then the HC23O2. And she's going to do the same with Congo red, and then at the end you're going to mark down all the different colors. So now we can see all of the solutions. They've had their indicators added. So just remember, in the front row we've got HCl, all 5 of those. In the second row we've got NaH2PO4, and in the third row we've got HC2H3O2. And then in the first column here we've got bromcresol green, Congo red, methyl yellow, thymol blue, and methyl yellow, or methyl violet, or violet at the end there. And these are all the different colors that we're getting in each of these wells. And I'm going to go ahead and put this above here so we can get a better shot of all of these different colors. So now what Teresa's going to do is she's going to clean off the well plate into the waste beaker. She's going to do that just by, first of all, pouring the stuff in. Hold it upright so everything goes in the beaker. There we go. And now what she's going to do, she's going to grab the DI water and she's going to clean out each of those well plates. And then after that, she's going to dispose of the waste per the directions of her instructor. So this is for part B here. And what I'm going to do is show you how you can figure out a pH range based on different colors of indicators. And we're using this diagram, which you can find in your lab manual. You find it on the first page of your lab manual, I think, on the pH and buffers lab. And what I'm going to do is show you how this relates to the colors that we're getting here. I'm only going to show you HCl. You do have colors for these as well in your results, and you should refer to those in order to figure out the pH ranges for those. But I am going to show you how to do the pH range of HCl. So this one right here is the one we're going to focus on. Alright, so let's look at bromcresol green first. You can see that we have a yellowish color here. And then if you look at the pH scale for bromcresol green, you can see that to be yellow, it's going to have a range somewhere between 0 and 3. So I'm going to go ahead and write that there, 0 to 3 for bromcresol green. What we're trying to do though is zero it down or sort of get it into a 1 pH range, like 1 to 2 or 0 to 1 or 2 to 3 or 3 to 4 or whatever, based on what we're seeing here. But we do know it's going to be between 0 and 3, so we've already narrowed it down a little bit. The next one, Congo red, you can see that it's a purple color, and you can see again that based on this diagram it's probably going to be between 0 and 3 as well. Now methyl yellow, you can see is red, that looks like it's between 0 and 3. So all of those three are really telling us the same thing at this point. Now thymol blue, it looks like a purple color, which would give me the suspicion that it probably wasn't between 0 and 1, and it's probably not between 2 and 3. It's usually in these color transitions that we see weird colors occurring. For thymol blue, that purple is a little bit unexpected, but I would just go with that for a start and say, well, it's probably between 1 and 2 if I had to guess. Since it's not red, it's not yellow, it must be somewhere in between in that transition area. Now as for the methyl violet, and again you've got a green color here, and we've got purple over here past 3 and going from 2 onwards, I guess. So upwards from 2 to whatever is going to be purple. Now you can see it's green, it's not yellow, so again I'd be looking at transition and be thinking it's going to be about 1 to 2. That would be my guess there. Now one thing that can be helpful is the rainbow colors, if you're familiar with them. Red, orange, yellow, green, blue, indigo, violet. And when you've got something like a yellow and purple, yellow and blue makes green, so you can see that yellow and purple could make green as well. So that might be interesting for you to look at. But if you got yellow and you got purple down here, you know it's going to be somewhere in between if it's going to be mixing. So that's a thought you might be able to use there in order to identify these different pH ranges. Alright, we're looking at part C. So what Chow's going to do is she's going to measure out 15 mils of acetic acid. That's HC2H3O2. That's the acetic acid. Now it doesn't have to be, well, yeah, let's try and get it as close to 15 as possible. You notice she's using a 50 mil graduated cylinder, and the reason for that is because we're going to add 30 mils of water in a little bit. But let's try and get it fairly close to 15, please, Chow. So she's just squeezing it in now, getting it up to 15. She's going to put it in that beaker that's in front. Probably a good way to arrange it. Then they're going to be mixed at the end anyway, so they really probably don't have to be labelled even. Of course, when we're measuring with a graduated cylinder, we want to try and make it so the meniscus is on the line. So she's going to try and arrange it so the meniscus is on the 15. Okay, that's really good, thank you. Okay, so she's going to go ahead now and close that back up, and she's going to pour that into the beaker. Okay, now what she's going to do is she's going to rinse that graduated cylinder out into the waste beaker with a little bit of DI water. Wouldn't worry too much about it being completely dry. And now she's going to add the sodium acetate. Would you please bring the sodium acetate up to the camera here? You can see a little bit lower, there we go. NaC2H3O2, that's the sodium acetate, that's the conjugate base. So go ahead now and add 15 mils of that, please. A little bit lower, please, Chow. There we go, thank you. Okay, it looks pretty good. So she's going to pour that into the other beaker. Alright, so now we've got our buffer components. Now she's going to make the buffer by pouring one into the other, is that correct?
Yeah.
Okay, let's go ahead and do that. Alright, we're going to measure the pH before we put the 30 mils of water in. She's turning it on. There we go. Now this one, she's going to just pull that off, that's okay. And she's going to measure the pH. So once that stabilizes, they'll get a pH measurement. And generally, wait about a minute, and if it's still going up after a minute, just take whatever value happens to be on there at the time. That should usually be plenty of time for it to stabilize. Alright, that looks pretty stable. So now what Chow's going to do, she's going to rinse it off. Rinse off the probe with DI water. And she'll put the probe back in its house just by slipping it back on. There we go. And she'll let it sit. Alright, now you're going to add 30 mils of DI water. And we're going to take the pH again. Is that correct?
Yeah.
Okay. Now we're not expecting a huge change in the pH here when we add the water, because all the water is going to do is dilute the entire solution. So go ahead and put that in. And it says here to mix it around a bit. We have a stirring rod handy in order to do that. And if you get a paper towel, please, we'll use that to wipe off the stirring rod. Place to put the stirring rod, just go ahead and put the stirring rod over there. Okay, cool. Now she's going to measure the pH of the solution again after adding 30 mils of DI water. As I said, we're not expecting a huge change here. So let it sit for about a minute and we'll see what kind of pH reading we get from that. Alright, so Chow's going to take the probe out of here and she's going to wash it off and put it back in its house. She's just rinsing it off there with some DI water and sticking it back in its house. There we go. Good job. Now what she's going to do, we've got that solution there. It's a solution of acetic acid and the sodium acetate with 30 mils of water. She's going to pour half of it into that second beaker. Just sort of split it between the two, equal amounts. There we go. That's good. Alright, thank you. Now what we're going to do is add some 5 drops of sodium hydroxide. Okay, 5 drops of sodium hydroxide, please. Add it to the first one. Okay, let's get a stirring rod and stir that around, please. Okay, now take it out. Now Chow's going to measure the pH of this one we just added the sodium hydroxide to. I'm expecting a small jump in pH. That's good. Let's go ahead and stick it in. I'm expecting a small jump in pH upwards relative to what we started with. So you took the pH of the solution before you added the sodium hydroxide, and now what you're doing is taking the pH after adding 5 drops of sodium hydroxide. That looks like it's stabilized. So leave it in there, please, Chow, and go ahead and add 5 drops of HCl, there we go, to the other one. Okay, good. Let's stir that around the stirring rod, please. She's rinsing off the stirring rod. That's very good technique. Alright, just giving it a bit of a stir. Alright. Now in between, she's going to take the probe out, rinse it off with water, DI water, and then stick it in the other solution. Very nice. Okay. Let's go ahead and stick it in the other solution and take the pH. I expect for this one we'll go down a little bit based on what we had originally started with. So now Chow is going to clean off the probe with DI water and put it back in its house. So now what Chow's going to do is she's going to make up an uneven buffer solution. So 2 mils of the acetic acid she's going to put into a graduated cylinder. I recommend a 10 mil graduated cylinder for this part. So she's going to add 2 mils into that, making sure that the bottom of the meniscus is on the 2. Okay, that's good. Let's pour that into the beaker, please. To the other graduated cylinder, she's going to add sodium acetate, 20 mils. So we've got 2 mils of the acid, now 20 mils of the conjugate base is being added. Okay, that's great. Now go ahead and add them together. Let's give it a little bit of a stir with the stirring rod, please. Okay, cool. Alright, let's put the probe in and measure the pH of this uneven buffer solution. So we'll wait for a minute and we will get an idea of the pH here and wait for it to stabilize. Looks like it's already stabilized, so we'll go ahead and mark that down. Now what I'd like you to do is rinse off the pH meter, put it back in its house. And we're going to add, is it 3 mils? Yes, 3 mils of sodium hydroxide, please. So use the 10 mil graduated cylinder. She's rinsing it out with a little bit of water. It's good, good technique. And now she's going to add in 3 mils of sodium hydroxide. And again, she's going to make sure that the bottom of the meniscus is on the 3. Now what we're going to see happen here is this is an uneven buffer mixture. So what's going to happen is the addition of this much sodium hydroxide is going to cause the buffer to overrun. So I'm expecting a fairly large increase, in this case, of pH based on what we saw previously when we were adding a small amount to an even buffer solution. So the sodium hydroxide is going to eat up most of the acid that's in there, and we're going to end up getting a large jump in pH. So well, let's see if that happens. So go ahead and add that in and give it a little bit of a stir around with the stirring rod, please, Chow. Then of course what she's going to do is take the pH of that solution. So we'll take a look at that, and you probably can't see the pH from here, but it's going to be a pretty big jump when we do this. So we'll wait for it to stabilize a little bit. Pretty stable, so we'll go ahead and take that result. Alright, Chow, I'd like you to take the pH meter out and clean it off and put it back in its house, please. Put that beaker off to the side, please, one we just worked with. And now we're going to work with the next one. And we're going to do exactly the same thing as we did previously. We're going to add 0.1 molar acetic acid, just cleaning out the graduated cylinder first. So 2 mils of acetic acid. Then she'll add 20 mils of the sodium acetate to that. And this time though, we will add 3 mils of HCl, and we'll see what the pH change is going to be. Notice that we're making up a new buffered solution here. Right, very nice. Now she's going to stir it up a bit, that's okay. Now she can add the 3 mils of HCl. No, we don't need to take the pH, we've already taken the pH of that solution once. We don't need to do that again. Now she's adding the 3 mils of HCl, cleaning out the graduated cylinder first. And again, ensuring that the meniscus is on the line of 3. Okay, go ahead and add that into the solution and give it a little bit of a stir, please, Chow. Going to take the pH of that solution. So what we're expecting here is a somewhat smaller drop in pH as we take the solution that has a fair amount of conjugate base in it and we're adding not very much strong acid to it. So some of that will be eaten up, but we're not going to see a huge drop in pH. Now what we're going to do is we're going to have 2 25 ml samples of just regular garden variety water. So Chow, please go ahead and fill up that 50 ml graduated cylinder. She's just going to fill pretty much close to the top graduation. We're not too concerned about the exact volumes here. Alright, that's good. Alright, pour a little bit out, so we've got 50. There we go. Now she's going to pour about 25 into the first one and about 25 into the second one. Doesn't have to be exact, but anywhere in that ballpark is good. Now what she's going to do is she's going to take the pH of regular water. So we're going to get a value from that after about a minute. That looks like it's stabilized. That's good. So go ahead and rinse it off with DI water, because we like to do that. And we'll put it back in its house. Right, to the first one, you're going to add 5 drops of NaOH. Now this one is not a buffered solution, so I'm expecting a pretty big jump in pH when we add the probe to it. So go ahead and give it a bit of a stir too, please. Okay. Okay, so we'll get the pH. While that's stabilizing, she's going to add 5 drops of HCl to the other beaker. Yeah, it does look like there's a pretty big jump in pH here. Alright, that looks like it's stabilized, so we'll go ahead and clean that off and stick it into the other beaker. Now for the other one, since again it's not buffered and we're adding HCl, we're expecting a pretty big drop in pH relative to where we started. Did you give that a bit of a stir too, please? So let's stir that up a bit. There we go. That's much better. Alright. Yes, and we're observing a pretty big drop in pH here. Yeah, don't forget to stir it when you do it. And that looks like it's stabilized as well. It's good. So this is to help you out with part C. So you're going to get a whole bunch of data here, which will be pHs that you'll get off the pH meter in each of these instances after preparing each of these systems, some of which will be buffers and some won't be. So when we're talking about the first part here, we're looking for the pKa of this weak acid 15 mils to conjugate base buffer system. So it's 15 mils and 15 mils. First of all, let's look at some terminology here. And if we have an acid, generally we're talking about a weak acid here. That's why I've got that in parentheses above the acid part. We also couldn't call that the conjugate acid as well, which means just simply partner acid to the base. And in each instance, what they all have in common is that when you put them in water, they all produce H plus as ions. And you can see that HA, HB, HC2, H3O2, these are all representations of a weak acid that you'll use in this lab. As far as the bases go, what they all have in common is they react with the water here, and you are going to have the water in here to act as a source of OH minus, and they produce OH minus and actually the conjugate acid as well as products, but it's the OH minus that's more basic in all of these instances. In this case here you've got NaOH, which is really just Na plus and OH minus, so just be aware of that when we're considering it. So those are all considered to be conjugate bases down here, and these are all considered to be conjugate acids or weak acids over here. So we've got over here the 15 mil weak acid, 15 mil conjugate base buffer system. If you're looking for the pKa, which will be a measure of the acidity of the solution, then we can, well, the power to make something acidic, I should say, that pKa value, we can use this Henderson-Hasselbalch equation to achieve that. The pH you'll get from over here, and that will go in as the pH. Then you've got these two possible equations you can use. You can do log of concentration of A minus over concentration of AH, or if the concentrations are the same, which they are in this case, then we can use volume of A minus over volume of AH. So we actually do have the volumes here, 15 mils and 15 mils. So we can sub those in here, and we know that the base is going to be the A minus part, and the acid is going to be the AH part. So we know which one goes in which place here in this Henderson-Hasselbalch equation. So that's how we can figure out what the pKa is, given that we will have the pH from over here. We can do the same thing on the diluted buffer system. Now I'm not expecting huge differences between these two values once you find them off the pH meter, and we again can use that same equation in order to determine that. And you might say, well, we're going to add 30 mils of water. Well, the 30 mils of water isn't going to make a difference. So we've still just really got 15 mils and 15 mils of the 15 mils of the weak acid, 15 mils of the conjugate base. So really the water's not going to make any difference, and we can still apply this formula using those volumes that we have at the top there. So it's not really going to make much of a change to your pKa calculation. Alright, so after you've made this buffer, which is going to be pretty much equal amounts of A minus and AH, we're going to add sodium hydroxide to that and see what kinds of changes we're going to get to the pH. And a spoiler alert,
we're actually not expecting a huge change here in pH. Now, since we're adding sodium hydroxide that's basic, I do expect it to go up by a little bit, but not by a whole lot. And likewise, if we add HCl to the same buffer solution, I expect it to go down by a little bit, but not by a whole lot. So what's going on here is you've got this strong base, this NaOH, being added to the A- and AH solution, and your first thought's got to be, well, what's it reacting with? Well, given that NaOH is really just Na plus and OH minus, and HCl is really just H plus and Cl minus, the Na plus is going to be a spectator here, and all we're really interested in is what the OH minus is doing. Now, looking at that, I don't think the OH minus is going to react with the A minus, but I do think it will react with the AH. And if it does that, you'll get water and A minus, so water and that conjugate base. Now remember, the OH minus is incredibly basic. It has a pH of 14, the initial solution. I mean, that's hugely basic. This weak conjugate base here, though, these have a pH of around 9 because it's weakly basic. And the acids here will have a pH of around 5 because they're going to be weakly acidic. So we're not expecting huge jumps here in pH because we're using up the OH minus, and all we're doing is forming A minus here as a product which is weakly basic. Likewise, over here with the HCl, we can see that the H plus probably isn't going to react with the AH, but I can see it reacting with the A minus. And if it does that, it'll form HA, which, as I discussed earlier, is weakly acidic. Whereas H plus over here, NaOH, that has a pH of about 14. And the HCl here will have a pH of around 1. It's a strong acid. But you can see that the HCl gets eaten up by the A minus, because we're not adding huge amounts of HCl here, certainly not enough to react with all the A minus, which means we're left with HA over here. And that should give you a good indication as to why we don't get those huge drops in pH or huge rises in pH we might be expecting if we add portions of strong base or strong acid to these buffer solutions. Now, if you've got a situation here, though, where we've got this 2 mils of weak acid to 20 mils of conjugate base, schematically it might look something like this. You've got AH, which is your acid, then you've got the weak acid, the A minus, which is the conjugate base. But look how much A minus there is going on here. And you can see that when we add the sodium hydroxide to that, it would be pretty easy to overrun the amount of AH that we have here and be left with the AH disappearing and getting a whole bunch of OH minus in the solution, which would lead to a pretty drastic rise in pH. So I could see that happening, and that's probably something that you would actually see here. And what you're using here is this data. And let's see, I'll just put that down here. Yeah. And that's what you're looking at. You're looking at the pH of the initial buffer system, and then what happens after you add the NaOH. And I would expect that if you add the HCl to that, then you're not going to get much of a drop in pH because there's a whole lot of A minus here to react with the HCl. So I wouldn't expect to see that. You're not asked about that, but I wouldn't expect to see a huge drop in pH here relative to what you see up here. Alright, the next thing you're going to do is you're going to take deionized water and just add straight HCl and straight NaOH to just regular deionized water. Now, if you'll notice here, there's nothing in the water to react with the HCl or the NaOH, so I would expect a pretty drastic change in pH by adding straight HCl to water, and I'd expect a fairly drastic upwards change in pH by adding sodium hydroxide to straight water. Again, they're not reacting with anything. Contrast that with these situations where you're adding sodium hydroxide and HCl to buffer solutions, and you can see you're not going to get huge changes in pH. We saw this up here when we made the comparisons with the data that we saw. So all of this is with reference to what we're going to do down here.
This is part D of the pH and buffers lab. So what we've got here, out the front, we've got an unknown. It's got a certain pKa associated with it. We know that pKa because it's written on the bottle. And next to that, I've got a graduated cylinder with 20.0 mils of that acid inside it. Additionally, we have a burette here. And in this burette, we've got 0.1 molar sodium hydroxide, and it's up around the 0.00 mark. Now what Samuel's going to do is he's going to pour in the acid. Hang on, I'm going to zoom in here a little bit. There we go. He's going to pour the acid in to this beaker. And that's good. Now what he's going to do is, oops, no, you need to take the probe out of his house there, Samuel.
Oh, I'm sorry.
So you'll do that by just taking it straight off. You can just, you don't have to unscrew it. There you go. That's good. All right. So put that in there. Alright, that's good. So the probe's in there now. The pH meter is on and it's reading a certain value, but we're not going to say what that value is right now. Suffice it to say that we're going to be adding sodium hydroxide and using the stirring rod to stir the solution, and occasionally checking the pH until it gets to the target pH that your instructor has given you. So you've got the pKa, you've got the target pH. You should have already calculated the amount of sodium hydroxide you think you should need, and we're going to verify that that is the exact amount that, or close to the amount that you'll need, by actually doing the titration and getting to that target pH on the pH meter. Alright Samuel, so go ahead and start adding the sodium hydroxide. So add it at first in say 5 mil, or at least a couple of mil increments. Stop there for a second. Yeah, so just add 5 mils. Give it a bit of a stir around. Now if necessary, hold up the pH meter a little bit. There we go, and then stir with the other hand. There we go, it's better. That's probably good technique. Now some people like to use the pH meter to stir with. I'm not a real fan of that. It's a probe, it's not a stirring rod. It's good. Alright, take a look at you should always be monitoring the pH meter as well to make sure you haven't overshot the target. And it haven't yet, right? No. Okay. So what we're expecting obviously is if we're adding sodium hydroxide, we're expecting this pH to go up. So add a little bit more to stop there. Monitor the pH, make sure you haven't overshot it yet. Alright, you're still a fair way away?
Yes, I am.
Okay, good. Now I think from this point he might want to slow it down a bit. So he's just going to do a slow drip, 1 drop at a time, Samuel. There we go, that's good. And now he's going to stir it and continue to look at the pH meter, see what's happening to it. Does it seem to be a fair way away?
Yes.
Okay, if in that case, then go ahead and add another full milliliter. Give it a stir. How are we looking now? Still a fair way away? Alright, add another full milliliter. Okay. Yeah, go ahead and add another milliliter, Samuel. Looks like we're getting close to our target. So what do you reckon? Are we about 0.1 away now?
Yes.
Okay, so let's go ahead and just add it drop-wise, 1 drop at a time. Okay, now stir and monitor the pH meter at the same time. over there. Oh, there. Okay, stop it. And there we go. So what's going to happen then is that Samuel's going to read off the burette how much sodium hydroxide has been added, and then that's hopefully comparable to the value that we just calculated earlier for the amount of sodium hydroxide that needed to be added in order to get to our target pH.
So what I want to do now is give you some guidance on how to do Part D. Now there's two ways that one can prepare a buffer. In Part D we're going to use a second method, and I'm going to show you the first method, which is kind of related to what we did in Part C. And in Part C what we effectively did was we took a beaker that contained B- and a beaker that contained BH, and we added them together into another beaker that contained a mixture of B- and BH. Let me give it something bigger here. So remember that a buffer consists of a mixture of a weak acid and its conjugate base. And per the terminology that I had from Part C, you can see that HB or BH is going to be your conjugate acid, and the B- is going to be your conjugate base. So both of those are present in the solution, and that's how that was made. So it was made by adding B- and BH together to form that buffered solution. So if you wanted to do some math here to figure out how much of a certain base you would need, that's the NaCa-C2H3O2, as you can see here, that's the weak base, and here you're given an amount of acid here, then we can apply this formula in order to make this work out. Now, since both of these do have the same concentration, we've got 0.1 molar and 0.1 molar, then we can go ahead and use this second modified equation, which is going to make it a little bit easier on us, where we do pH equals pKa plus log of volume of B- over volume of BH. Now, as I said earlier, the B- is going to be the same as the NaC2H3O2. And we know that because that's the terminology I gave you previously in Part C. Now the pH we're given as being 5.78, and the pKa we're also given as 4.73, and we've got the volume of B- is what we're looking for, and we already have the volume of BH, and you can see here BH is going to be the HC2H3O2, this one here, and as you can see it's here as well. BH and HB, by the way, are the same thing, so that'd be over 20.0 mils, and now you can see it's not too bad. We're now able to go ahead and solve for that. Now if we isolate this by bringing it over to the other side, so we subtract 4.73 from both sides, we'll be left with this. 1.05 equals log of volume B minus over 20.0 mils. Now in order to get rid of that log, what I'll have to do is do 10 to the power of on each side, and that will get rid of a log on this side. And then of course volume of B minus will be 10 to the 1.05 multiplied by 20.0 mils, and I get 224 mils as my answer there. Alright, so that's how you do it if you were just simply adding B- to BH. But that's not the only way that you can make a buffered solution. I'm going to go ahead and get rid of all that working there for that one. The other possible way of producing a buffered solution is to take, and this is what we're going to do in Part D, is we're going to take a solution of BH and we're going to add to it a certain amount of OH minus, but the OH minus is going to be less than the amount of BH that's in the solution. So let's say we do add 2 OH minuses. What's going to happen is we're going to end up with B minus, B minus, BH, and BH, which again is the buffer solution. Now the logic behind that is that the BH plus the OH minus produces B minus and H2O. But I want you to see that if you started out with 4 molecules of BH and then you added 2 molecules of OH minus, you'd end up with 2 molecules of B minus, and we would also end up with 2 molecules, 4 minus 2, of the BH. So the whole point of what I'm trying to get across here is that we can still use this same formula where we've got pH equals pKa plus log of the volume of B minus and the volume of BH. Now everything has the same concentration, 0.1 molar, so we can just go ahead and use the volume formula here that we used above. But we know that after the reactions occurred, we can adjust this. It'd be pKa plus log, and the volume of B minus will always equal the amount of OH minus that was added, because the OH minus reacts with the BH to form B minus, so that'll be volume of OH minus there, over the volume of BH, and because the OH minus is reacting with the BH, the volume of BH initial here minus the volume of OH minus. So that would be the final formula that we would have to use in order to calculate a volume of OH minus that we were adding. So let's say we were assigned a buffer of pH 8.0. This will be in your Part D procedure. Let me make that a little bit clearer. So that would be the buffer pH, and the pKa, you'd have to be given this by the instructor as well. But let's say it was 7.0. So what we can do is we can go ahead and we can use this formula here that I've got down here in order to calculate the volume of OH minus we'd need to add in order to get a pH and a pKa that we were looking for, that we were assigned. Alright, so let's go ahead and get rid of some of this stuff here. And I'll move this up here, and I'll get rid of this other parenthesis here. Okay. So let's do a little bit of we'll do a little bit of math here based on what we've got. Okay. So the pH is going to be 8.0. The pKa is going to be 7.0. Remember, these are values you'd have to be given. And what we're going to do is we're going to let the volume of OH minus equal this variable y. It'll make it a little bit easier. So it'll be Y over volume BH initial minus Y. And what we're effectively doing here is solving for Y. Now this volume of BH initial, we're actually told that, and it's here in the procedure, because that's going to be 20 mils of the acid solution. So he says there's on unknown acid solution, that was a BH that we were talking about earlier. So it'll be 20.0 mils that'll go in there. So now we need to solve for Y, and you see now it just becomes an algebraic expression. So 8 minus 7, that's going to be 1.0, is equal to log of Y over 20.0 minus Y. And then to get rid of that log, we do 10 to the power of on each side. So we end up with 10 to the 1.0 equals Y over 20.0 minus Y. And that means we've got 10 times 20.0 minus Y equals Y. We distribute that throughout that, so 10 times 20.0 is going to be 200 minus 10Y, which equals Y. Now in order to get the Y's together, we bring them over the other side, so we'll have 200, that's 200 mils, 200 mils equals 11Y, so Y would equal, I get 18.2 mils. So what does that represent? Well, it represents the volume of OH minus you'd have to add in order to make that pH solution from an acid that was 8.0 on the, an acid that was 7.0 on the pKa. So you're making a pH of 8.0 out of an acid that has a pKa of 7.0. And that would be the amount of OH minus you'd have to add in order to make that buffer solution. Remember, this is just another way of making a buffer. Alright, so that's how you'll do it. Now, you will also do this business here with the burette, and you'll get certain volumes of OH minus, and the volume of OH minus used in the experiment will be the difference between those two. And then you'll see if it agrees or not with the calculation that you come up with over here based upon data that you would be given by your instructor on the pH of a solution and the pKa of some unknown acid.